Now, as Rutherford continued doing these experiments, they were able to change the kinetic energy or change the velocity of those alpha particles and shine those rays of alpha particles at gold nuclei and take a look at how that change in kinetic energy affected scattering angles. And if you look in the Tsokos text, you're not going to have to memorize that. There's a formula in there where he was able to predict mathematically what that scattering angle should be based on kinetic energy or velocity of electrons coming in. And as they change the experiment, it forms a quite normal inverse relationship according to his formula. And this will be Rutherford's formula to predict what that angle would be, and it forms a nice relationship. And as he increased that velocity or kinetic energy of those alpha particles, once that kinetic energy got really, really fast, or not fast, or it got really high and the velocity got really fast, the distance of closest approach starts to approach a value of around 10 to the negative 15 meters. That would be the actual diameter of a nucleus. And the problem with that is once it gets that close, you should have like infinite repulsion, or as we learned in nuclear fusion, we could start getting into that area of where the strong force would be and get sucked in and fuse that nucleus. So Rutherford was able to actually get some really interesting results as he increased the kinetic energy of those alpha particles. There came a point where his graph deviated from what he expected to see from the scattering at 80 degrees. So as he went further and further and further, there comes a point at around 27.5 mega electron volts for the kinetic energy of that alpha particle. We get massive deviations. We don't get as much scattering anymore. Okay, so that's what we're starting to see, is that a strong force starts to interact with that alpha particle, attract it and deviate it from its trajectory of what we would expect. Okay, so this is the first graph that proved what Einstein predicted, is that there must be a very strong force holding that nucleus together, and here we can see it. Once we get to that kinetic energy, which we can calculate the radius would be around 10 to the minus 15 meters, we get massive deviations. So this is the first evidence that Rutherford provided that there is actually a strong force that is bound to the nucleus. And this is the birth of like quantum mechanics, the strangeness of physics at the nuclear level, where all of a sudden at the nuclear level we have forces that are at play that aren't at play in our life, these meter scale dimensions that we live in on an everyday basis. So classical physics talks about physics in the meter scale, and nuclear physics or quantum physics is talking about interesting new physics that is occurring at the 10 to the minus 15 meter scale, or the nuclear scale. All right, so here is just the graph that shows the example of that strong force. So this often appears on exams, or a question showing what is the evidence for the strong force. You have to describe this experiment. So be worthwhile reading and making sure you understand that. And then after we discovered the nuclear radius and we can change the material and do these experiments, we can actually start to look at measuring the radius of different materials, different atoms, and looking at relationships of how a change in the atomic number actually affects the radius. And when we're shining alpha particles, protons that repel, it's difficult to do that experiment because you're getting repulsion. So another way of measuring the radius of a nucleus is to use particles that won't interact with the nucleus, such as neutrons or such as electrons. Okay, so if I shine a neutron, or if I send a ray of neutrons at a nucleus or an atom, and I can change the energy of that neutron, I can then basically see how does that neutron or electron diffract as it goes around a nucleus. Let's see if I can find a nucleus here. Yeah, so how would a neutron diffract as it goes around that barrier? And that's another type of experiment where we look at electron and neutron diffraction. And we've seen this before when we talked about matter waves with electrons. I showed you guys examples of electron diffraction. Well, we can have electron or neutron diffraction. And here would be that classic graph that I showed you for electron diffraction, where it really obeys single slit diffraction. So when I find this first minimum, that's that minimum intensity, okay, that would be the central max, that would be my first minimum of diffraction. If I measure the angle to that minimum that the detector forms, that angle corresponds to this diffraction formula that we used before for destructive interference. 1.22 would be for circular diffraction if the diffraction patterns are circular. If the diffraction patterns are not, then it would be just lambda over d, this one over here. So whenever a question arises that they want you to ask for nuclear radius or the diameter of a nucleus using diffraction experiments with electron and neutrons, you usually would be given a graph like this, and you have to interpret the information from the graph. So if I can measure the angle to the minimum on the graph, like over here, 42 degrees, I can simply just plug that into one of these formulas, depends on, they'll specify whether it's circular or not circular. So if I plug that into here, 42 degrees, sine 42, and I need to know the wavelength of that electron. The only way I can know that is if they told me the momentum of that electron or the energy, and then I can calculate the momentum from energy. And then I'll be able to determine the wavelength using the de Broglie equation. And from there, I would be able to calculate d, and d is the diameter. So d would be the diameter, and when you do these calculations of diffraction, you would find that the diameter is indeed 1 times 10 to the minus 15 meters. All right, so that's experimental evidence between Rutherford's alpha particle and these electron and neutron diffraction experiments for the size of a nucleus of an atom. Now, what can we do with that? Well, we can, as we explored different materials, we came up with a mathematical relationship that describes the radius of any nucleus, and the radius of any nucleus is proportional to the product of a constant, okay, that minimal radius, which probably the radius of a hydrogen atom, all right, times the mass number of any nucleus to the power of 1/3. All right, so it's not directly proportional to the mass number. There's an exponent to it. Okay, so if I know the mass number, for example, if this is gold 79, I can plug 79 in for here, and then I would be able to find the radius of a gold nucleus. Well, a common IB problem that results from that is to this one here, where we need to show that all nuclei have the same density. Okay, we could see that nuclei have different radii, but why is it that all nuclei have the same density? Well, you can prove that pretty easily by understanding what the density formula means, mass over volume. And we know that volume is equal to 4/3 pi r cubed. So if you want to pause, you can try to understand how if I plugged in this formula over here for radius, and then I try to substitute back into here, I bet you I can find out that the density of all nuclei would be the same. So after unpausing, you can see the mathematical relationship here. The mass of any nucleus is related to the atomic mass number times the mass of a single nucleon. So if I knew how the total number of nucleons in a nucleus, and this is the average mass of a nucleon, I can multiply it together to get the mass, and then divide by 4/3 pi r cubed, and r, this is the relationship for r of a nucleus. Now, once I cube that, okay, I will then get a. So these a's are going to cancel out. And then what I end up getting is the density of any nucleus is just a bunch of constants. So that constant divided by 4/3 pi, the radius of a hydrogen atom to the power of 3. Okay, so for some reason, the density of all nuclei predicted to be exactly the same, and that density would be this. So this is a very common IB problem that would appear. That would, if you'd be lucky if it does, because it's worth like three or 4 marks, and all you have to know is how to plug all that in to prove this.